All right, you crazy kids, we're on day 2 of direct variation. Remember, that's y equals kx. So what I have for you is just a little warm up, getting the routine of what we were doing before. So if 5 equals k times 10, right, we need to find out what that k is. What's constant of variation? The k is 1/2, and then it says find y when x is 11. So I'd start over, I'd say y equals 1/2 x. They told me x is 11, so I want to know what half of 11 is. So y turns out to be 5.5. All right, we can repeat the process with the next two. And we want to make sure we can determine if it is a direct variation. Remember, it has to look like y equals kx. That means plus 0, right? That's why we did slope-intercept form first. I want to make sure that it has nothing else added onto it. So I can divide by 2, and that works out nicely, but I still have this 1/2. So is this a direct variation? The answer is no. Or as an old friend of mine used to say, nah, not going to happen. All right, so in the other one, we got 6. So we got y equals negative 2x. Is that a direct variation? Sure looks like it, right? I could write plus 0 on here. I don't need that. So if I can say yes, then I go on and say k equals negative 2. So that's our first exercise as we take a look at these. So I want you to pause the video, go through the first section here, and see which ones are direct variations. And if you can say yes, if it is, you have to say k equals what number? That was the pause for you to pause the video. All right, now we're back. So number 1, we said yes, and k equals 5. And number 2, we're going to say yes because this 0, right? We're going to move some things around, right? I might say 2y equals negative 8x. So y equals negative 4x. So yes, again, k is negative 4. And number 3, no, there's no way to get rid of that negative 7. That's not going to happen. I can move it to the other side, but it doesn't get rid of it. Remember, that's what we're after. Here, I'm going to add y to the other side, right? So I'm going to make it look like this. So that's a yes. What's k? K is 3. Number 6, you can imagine a plus 0 in here, so it works out. Yes, k is 3/5. In number 7, what happened to number 4? Anyway, all right, so we're going to add 3x over, so I get 2y equals 3x. I'm not sure yet. Oh, divide by 2. Oh, there it is. That's k. K equals 3/2. That's a yes. That's a direct variation. In number 9, hopefully you get the idea now. I can move the 8 over. I can divide by 4, but this is still going to be 3 in the end. So this is a big no-no. That means I can jump to 11. The 6 tells me that this is not going to happen. All right. Now, there are ways to try and trick you when there's extra stuff, but I'm not trying to do that today. All right, so in the other one, I'm going to add 3x to the side, so it becomes equal, divide by 3. Yes, this is, and k equals 2. So we have a direct variation going on here as well. Remember, direct variation is slope-intercept form, but it always goes through 0. All right, so the next thing, and I said in the other video, we're going to work on some problems that you may use at some point, and this is the type of problem. It's a word problem. These happen in the real world. That's real lightning. Ow, I'm just kidding. It's not real. You can touch it. It's all right. All right, what we're looking for, your distance from lightning varies directly. That's what you're looking for. If you draw a box around it, that's the good stuff. With the time that takes you to hear the thunder. All right, so your distance equals k, right? Because this is where equals k will go. Wherever you find varies directly. And after that is going to be time. So time seems like a good thing to put here. If you hear thunder 10 seconds, 10 seconds, is that a distance or a time? It's a time. So it goes in for time. You're about 2 miles. That's a distance. So 2's going here. All right, you know what to do. We're going to divide. K equals 1/5, or we could say 0.2. Either way. All right, so we're going to use an equation. All right, so distance equals 1/5 times time. So all I did is I took and put that value right here. Use your equation to determine the distance from lightning if you hear thunder 17 seconds after you see the lightning and the thunder. 17 seconds. I'm pretty sure that is a time. So that means it would be 17 over 1, so 17/5. So that means your distance is 17/5 miles. Because that's how we talk in the real world, right? Dude, did you see that boat? It's 17/5 miles out there. I hope they can make it in safely. No, that's not what we do. All right, so that's 3 That would get me to 15 2/5. All right, so that's 3.4 miles away. Can I use a calculator? Sure. I needed one. Need no calculator. Got one. All right, that's our lightning problem. You know, a good thing to do during a storm? I don't know either. But sometimes I make muffins because I get hungry. As long as the power doesn't go out, then your muffins get ruined. The recipe for a dozen muffins calls for 1 cup of flour. The number of muffins varies. Oop, there it is. Varies directly. That's what I was reading this for. Varies directly. Before that was muffins. The number of muffins. And after that is the amount of flour. All right. So muffins equals the constant variation times the flour we're going to use. Write a direct variation. Wait, where'd the numbers go? Where's the numbers at in this problem? A dozen muffins? Oh, dozen muffins, 12 equals K times 1 cup of flour. The constant variation is 12. All right, so what's the equation actually going to be? Muffins equals 12 times the flour. There it is. All right, now big storm, right? So you made 150 muffins. 150 equals 12 times F divided by 12 divided by 12. So how much flour do you need? Yeah, I'm going to need 150 twelfths cups of flour. Yeah, because that's how we do this. You know what I mean? Yeah, right. Go ahead, divide it. That's 12.5 cups, 12.5 cups. All right, so that's what we're dealing with. All right, you're going to need your calculator on the last one. I promise you, because this is some crazy stuff. Anybody wants to be in the Navy, thank you. If you want to go and defend our country, that'd be fantastic. Okay. The force you must apply to lift an object varies directly. And this doesn't have anything to do with the Navy. I'll tell you in a second. Varies directly. There it is. So equals K. All right, so here's what we got. We have the force you must apply. It varies directly with the object's weight. So there it is. All right, you need to apply 0.626 pounds of force to lift something that is 28 pounds. That's a weight. All right, to do that, we're going to use a pulley system. We'll talk about those in science class. Right, here it is in action. This is called a windlass. Windlass is what they use to pull up the anchors on major ships. It could be a cruise line. It could be something in the Navy. It could be anything that has an anchor that you want to use out there. That's called a windlass. All right, so it is a pulley system. Here's how it works. So if this is what's going on, we're going to divide by 28. All right, I want you to think about this. I'm going to take like 63 cents and I'm going to divide it amongst 28 people. Big number or small number? Really small number, right? 0.626 divided by 28. Boom. 0.02236. We'll cut it off there. So the force needed is 0.02236 times the weight. Now, it just so happens that I used to, lift 450 pounds at a time. Okay, I made that part up, all right? It's fine. I'm old. All right, here we go. 0.02236 times 450. All right, so how much force would I physically have to apply, right? Or how much force is needed with this piece of equipment? Right, that means you have to have about 10.06 pounds of force. All right, could you imagine that? So if you could pick up like 2 5-pound dumbbells over in the weight room or something like that for gym class, that would be, if we had a pulley system, that means you could actually move 450 pounds. All right, so science is pretty cool too. Not as cool as math, but we'll get there. Couldn't do the science without the math. That's all I'm saying. All right, see you later.